All right. So tonight's derivation is going to be pretty short and sweet, simple. All the good things you want in life are going to be happening today. So this is a pretty familiar problem, and it's pretty typical. You've probably seen it before, but it's going to be nice because you're going to recognize a lot of things as you go about. So first of all, I'm going to draw about the scenario. It's a very typical scenario. You apply some sort of velocity to an object. We're going to consider a point particle. It's going to have to deal with any rotation or anything. It's just something that's being shot out in whatever way you want. All right, it's a very generic problem. And then this follows parabolic path. Right? And it starts at point x naught, ends at point x naught, or x hat. And for the simplification, let's say that the initial position in both the y direction and the x direction is 0, just for simplicity, and because it just makes more sense, right? Just in general, because what we're trying to find here now is, okay, at what distance from me will it hit the ground? Or from the initial position, not necessarily from you, but wherever it started. Let me make this smaller. So let me just draw a little bit smaller. There you go. It's very small. X naught equals 0, and then we have xf. And what we're trying to find here is this distance here. We're going to know as r. So why not? Alright. So now let's do something. Before we jump right into finding what this r is, let's first explain our motion, right? So how can we describe our motion at a point? Basically, what are the equations of motions for this problem? That's something you want to deal with a lot, is what are the equations of motion? Well, first of all, here's a here's an assumption that we're going to make. Basically, what this is saying is that for every time t, the acceleration in the y direction is going to be the same for every point, right? So this would look like just a straight line if you were to plot this because, well, it's constant. It does not change. Even though realistically, if this were to be like the surface right here, and this were to be the ball following this path, it would change very slightly, but we're going to assume, for simplicity, that it's constant. This is in the y direction. Something else we're going to say, why not? The acceleration in the x direction, 0. So basically saying that nothing else is affecting it while it's in motion, so there's no friction due to air, because all the problems always say that. So, and it's also another simplicity thing, not necessarily realistic, but this isn't like in an ideal situation. So now we have this acceleration, but we need the other values as well. So we're simply going to integrate. This will be indefinite. This will not be definite because we need the general form. And instead of doing in the y direction, we're just going to say for both. But I'll show you what that shows up in a second. So we're just going to integrate. And by using our a value here, we know that in order to derive something to get a, there must be then another variable. It must be at least a single variable in this equation. So a, t. Since this will basically, in the derivation of this function, the t will vanish at some point. So if you were to derive, take the derivative of this with respect to t, it would then become a, which is what we're trying to find. But there is a little bit of a thing here I'll call constant integration, because there's another thing that can vanish from integration, and that is a constant. So if we were to take the derivative of this, at plus c, it would be still a. It would be the same derivative as just simply at. So maybe there's something there that we're missing, right? And we're going to call this all equivalent to V naught. No, okay. I have to give it a spoiler. This is the velocity, so we're just going to call it that. And so, in order to find this this constant here, we want to find the time at which this function is equal to c, and that, of course, is velocity 0 when time is at time 0 equals c. So we just found c, and we're going to denote that as v subscript o, as v naught. And so now we have an equation of motion. So for velocity, this is not necessarily, you can call that. So v of time t is equal to at plus v naught. Okay, and that's our v naught here. Right here is our v naught. Okay, so that's one of them right here. So what if we were to integrate this again? Let's do it one more time. See what we get. Anything juicy? Once again, we solve the process. Take the antiderivative of at. Get 1/2 at squared. Take the antiderivative of v naught plus v naught t. And once again, we see the same thing as last time, where we could take another there's another constant here that would act for this to be the same thing. So basically, it'll be equivalent with this constant with not, but we're going to find it. So let's try the same process. Okay, we're going to call this the position of the time. And so at x of 0, we're going to follow the same process just because to see if it holds anything important. We'd find that it's simply c. So same thing. We call that x naught. Alright, so let me get rid of all the junk and show what we just found. Oh, I just got rid of those, but okay. So we just found the a of t is a. Okay. Also found u of t is at plus v naught. Yet we also found x position of time is 1/2 at squared. I think I forgot the a last time. Anyway, plus v naught t plus that initial position. Okay, that's all good and all. I'm going to say for both directions, right? Now the difference is that this would be, yeah, it'll be different. Anyway, so this is like the general form of those equations. Now let's apply it specifically to this scenario. So in this specific scenario, let's do the x position of time. Okay. Now remember, the assumption we made is that the velocity is constant throughout in the extraction because there's nothing acting on it. So this term is 0 for this instance. So that just simplifies to v naught t. And remember how we said that for simplicity, we're going to assume that this is the initial position. So we're stating that this is the initial position right here, and that is 0. So it's simply v naught t. I like to put a little cursor because of addition. Gets in the way. And so that's one of them. Right. Yeah. Pretty much. Yeah. Also, if you were to look at, but if we do this in the y direction, now we're going to keep it in, if it were a Okay. So let's think about what exactly is R. What is R in terms of what we just found here? So we know that, well, first of all, I'm going to say that T star is impact time. So this is the time of impact. At time t, it touches the ground once again, right? So that must mean that x of t prime, or the position at x of t time, is r. So we can now need to find x of t prime. Now the issue is that we don't know what t prime is, right? Because if we were to substitute this here, we'd get v naught times t prime. But what we do know is that they share a common point at the final position. So the x position, or what we do know, is that if you look at this graph here, at the impact point, the y position is 0. So that's a known value. We know it touched the ground again, so it's at a position of 0. So if you look here at y of t prime, we know that it's 0, which we also know that it is this equation here, or this expression here. Now, do look at this carefully, because this should be v naught y. It's the initial velocity in the y direction. But all we need to do here is then solve for t. Now you could use the quadratic equation if you want, but that goes against the point of these derivations, and that's to use as little predetermined, pre-known things. So we're just going to simply factor this out. Factor it. So 0 is 1/2 plus v naught. They both have a common factor of t. So left with this, and of course, by solving it, you know that this whole expression is 0 at t equals 0, but we already knew that because it starts at 0. So we already knew this. So that's not necessarily what we want to find. We want to find the second time. What's the second time that this is 0? What is t in terms of these other variables? So of course we just then solve, and we get negative 2v naught over a time prime. That's star, should be star. R star, whatever you want. But we found an expression for the time at which it hits the ground the second time. So I'm going to erase some of this stuff so we have some more room. But we've basically done it. At this point, we just need to bring it all together. Right? So we found this. I'm going to erase that real quick. And then I guess an exercise for you, if you would like to try that, is using what we just found about T star. I'll put this over here. Oh shoot. Wait a second. 2v naught. Okay. So we found this. Now my exercise for you is to now use the definition of, well, it's pretty simple. But we need to keep in mind that this x of t, this is x, and this is y. So, if you look at our initial position, our initial velocity here, of course using simple trig, you find that v naught y is just sine theta, v naught, and v naught x is the cosine theta. But then using these, quite simply, you could find x of t. So we know then x of t prime. Oh yeah, this should. So I'm just gonna write in here. It's sine of theta. X of t stop. Just remember that v naught x or v naught that cosine of theta that we had before. And then we're going to, I guess I'll just do this. Then, using what we know about it, v naught cosine of theta times the sine of theta comes from right here. This would be squared 2. So it's negative 2 times v naught squared times cosine of theta times the sine of theta all over a. If you've done this before, if you've used the range equation, you know that this isn't exactly what it looks like, right? So, how then can we, is this wrong? Because let me tell you, this is correct. Okay? But, if you want to get it in the modern, the most used form, you need to look at this, well, I guess coefficient that way. Cosine theta, sine theta. Because you can rewrite anything in this form with any two variables, any two cosine and sine functions. You can rewrite them as follows. Right. Usually these are two different values, but in this case it's the same value. But you can still do it. And of course, this would cause this expression here to simplify to sine 2 theta from here, and then plus sine of the sine of 0 is 0, so be adding 0 if you wanted to, but that simplifies to this over 2. So what we just did is we rewrote cosine of theta times sine of theta as follows, and that will simplify quite a few things. It'll simplify both the 2 and make it use only one trig function instead of 2, because that would just be, I think that's pretty much why it was rewritten like that, so you could use it in terms of one function instead of 2. So, using that, you can then rewrite it as v naught squared sine 2 theta. Now I didn't explain really what theta was, but it's basically just the angle here that it's released at. Okay? Over A. That's probably very similar to what you know. Very similar to what you're used to. But the difference between what you're used to and what's here is that we haven't defined acceleration yet. Now, acceleration in this case, negative g. This is on Earth. That's negative g. So, you can resolve this to v naught squared sine of 2 theta all over g. Which everyone should be used to. So there it is. But another interesting question is, if I were to release this ball, let's say I'm in a competition with a friend of mine, and I were to release the ball as far as possible. I want to make it go as far as possible. So what then is r sub max? Now you likely already know the answer, but here's the derivation, here's where the intuition comes from. So if you look once again at our range equation, you see v naught squared sine of theta 2 theta g, right? So you have this, very typical. But these, the v naught and the g, are both constant. They don't depend, they're both constants. They don't depend on a second variable. Now this sine function is, well, a function, so it depends on a few things. Or a thing, really. Depends on this angle here. So let's look at this function. We know that there are constraints to the sine function in that it's less than or equal to 1. And we want to maximize this, right? So we want it to be at its most positive and greatest value. And that is, of course, 1. So at its most, sine of 2 times theta is 1, or sine of any function is 1. And we know that, let's think of the sine of x is 1 when x equals pi over 2. So no, it's 1 when x equals pi over 2. So that must mean that this is equivalent to pi over 2 as well. Right? And if you simply solve for that, the degree here, the angle, to find that max angle is pi over 4, or 45. So we deduced from the range equation, and since it has a sine function, there is a maximum, and everything else is constant. So to maximize the range with the same initial velocity, right, in the same areas, the same gravitational constant, it's all dependent on the angle due to the sine function, due to the angle of release, which I think is a pretty interesting thing. And the fact that we can deduce it just from a simple sine analyzation to know 45 degrees. So that's probably something you already knew, but this is more of an intuition as to why. And if you think about it as just, 45 degrees, 45 times 2 is 90, and 90 is like the maximum, so most top value. Remember, this isn't the angle. The one that we just found isn't the angle of release. That's when the value of the range is the most. Because of this 2, right? Because the initial angle is 45, not 1, but it maximizes it. Because if we were to do 1, you couldn't have an angle of pi over 2. Like that's why if you were to do pi over 2, it'd be kind of weird, right? Because then this would be maximized to the sine of 1 pi, which is to the left. So it's not all great.